Hello, good morning, everyone. My name is Mohamed Akram Mechter, and today we're gonna talk a little bit about orthopedic implants. So first of all, I will start with a short introduction in order to present the main problem that we have nowadays with orthopedic implants. Then we're gonna through the methodology and present it how I did to solve one challenge and propose solutions. Then we're gonna discuss the results together. And then finally, I will propose a conclusion and further works. Before going into the details, I need to define you, since I don't have how comfortable you are with the medical field, what is a plate type implant. Actually, orthopedic implant is a very wide category of all osteosynthesis solutions, including the one that you are interested in today, the plate type implants. The plate type implants basically are a thin plate made of stainless steel or titanium, and we can find some drilled holes or depth holes on the surfaces. Those holes, in case of a long bone fracture, will help the surgeon to create a bridge above the fracture, and then uses compression screws and locking screws to fix the bone, the plate to the bone. Thus, when the bone will be loaded, the forces will go through the implant rather through the bone, allowing the complete healing of this one. That's the theory. In the real cases, what happened is that several studies have reported the fatigue failures of orthopedic implant before the complete healing of the bone, inducing damages for the patient. Actually, if we go into the detail of the fracture of this implant, we found that the fractures always occurred from the vicinity of the hole. And if we look at the fracture surfaces, we found the typical fracture surfaces of fatigue failures initiated from the top of the holes. Now, since we know that a crack initiated from the hole, we are seeking a manufacturing project to improve the fatigue resistance of this region of the implants. One solution is to change the way that we drill the implants. The proposed solution is the flow drilling or the friction drilling. It consists in a rotative tool and the axial forces applied on this rotative tool in order to create friction, and this friction will heat the material. Not until approximately 700 Celsius degrees, allowing the tool to penetrate the material. And then when we remove the tool, we have a new hole. This hole have a specification such as upper bushing, a metal fiber rearrangement, and a lower bushing, but it's not what we're interested in today. When talking about friction drilling, this process widely used in a thin metal assembly, we are more looking to the secondary effects, which are work hardening effect, rearrangement of the metal fibers, and also the modification of the grain size. Now we have a hole, but as I introduced you, I need threads inside this hole to use all type of screws. We are going to study two different thread process. The first one is the most common one, the cutting thread process, which consists in creating a hole with removing the material. Those induced only a few effects on the microstructure, and we create chips during the process. The second process that we are going to study today is the flow formed threads or flow type threads. There is different denomination. This method consists in create threads without cutting the material, but by inducing a plastic deformation when the tool goes through the hole. This process induces also the secondary effects, such as a work hardening effect, and since we don't cut the material, there is no chips. All right, now we have holes, we have threaded holes, and we have two processes. We need to compare them in order to know if we are enhance or no the fatigue strength of orthopedic implants. Let's go into the methodology. We've shown that we have fatigue failures initiated from the holes, and we propose to use the combination of those two processes in order to enhance the fatigue failures of implants. To do so, from stainless steel bars, we created 15 samples by conventional method and 50 specimens by the flow form method. Then we performed a micro hardness test and also microstructural observation in order to know the impact of those processes. And then, following the ISTM A3A2, we performed fatigue test. More precisely, it was a 4-point bending test. Here, I just wanted to share with you the fact that we performed hardness tests and microstructure observation following transversal, here with sample 1, and longitudinal with sample 2 observations. Regarding the fatigue test, as I told you, it's 4-point bending test following the ICM-3A2, and we performed the fatigue test at 3 loading levels. And for each loading levels, we studied 5 specimens per manufacturing process. Let's now present and discuss the results. First of all, we start with the micrographic observation. Here, the first thing that we can notice is on your left is the conventional specimen, and on your right is the flow form specimens. For the conventional specimen, there are only few effects here for the first millimeters, and then we found equiaxed grain that is typical from this metal since it's from hot rolled bars. And for the flow form specimen, we know that the grain are deformed and also refined. If we now check if the grain and microstructure is accordance with the hardness measurements, we note that for the 0.5 millimeters for the conventional specimen, there is a hardness increase, and then we finally find the base hardness of the material. However, for the second processes, we found a hardness increase also for the first 0.5 millimeters, but after we have also an increase in the hardness until 2 millimeters, and after those 2 millimeters, we found the base hardness of the metal. If we combine those results in the same plot, we note that using flow forming process, hardness was increased by 250 Vickers at 10 micrometers from the whole surfaces, and we have a significant effect of the flow process up to 2 millimeters. Now, let's check if this positive effect on the hardness have an impact on the fatigue life of orthopedic implants. The third thing that we need to show is all crack initiated from the first threads counting from the bottom surface, which is in accordance with the 4-point bending test, since this surface is in tension. If you go now into the details, for the 2 first loading steps, we didn't note a significant difference between the average fatigue life of the orthopedic implants, because as I showed you before, there is a specific plastic deformation that induces the discontinuities on the flow form specimen, and those discontinuities will compete with the positive effect of the hardening and those inducing similar lifespan for the flow formed and conventional specimens. Regarding the last loading levels, we noted that the conventional specimen had a better fatigue life than the flow formed specimen. The main reason for that is, first, there is a difference between the crack initiation sites. When we look here at those images, we note that for the conventional specimen, crack always initiated from the tip of the threads, and for on your left here, for the flow form specimen, there is a pre-existing crack, which is a discontinuity induced by the flow process, and more precisely, by the flow tapping process. And these discontinuities at a low loading level, we drastically reduce the fatigue life of implant, since at a low loading level, we know that 80 to 90% of the fatigue life is to initiate a crack. So since we have a pre-existing crack, we are reduced the fatigue life of this orthopedic implant. The second reason for that is literature showed that a high level of strain hardening seems to have a detrimental effect on the fatigue life. And the third point, which is the last one, we noted that we found a sigma phase, which is arranged here in the flow formed specimen. And this sigma phase it's a brittle phase, and it seems to reduce the fatigue life also of the flow formed specimens. So now let's conclude about this presentation. We've noted first that we have a positive effect, which is very nice for orthopedic implants, but we didn't found that this positive effect matched with the fatigue life results. So I can basically say that in the actual manufacturing conditions, the flow process did not improve the fatigue life of the orthopedic implants made from stainless steel, 316 stainless steel. but we can suggest further works because the main differences and the main reason why we didn't improve the fatigue life was the presence of those discontinuities. And since those discontinuities are manufacturing process dependent, we can work on the manufacturing parameters in order to reduce the presence or avoid the presence in a perfect world of those discontinuities, and those purely take into advantages of the work hardening induced by these processes. Here are the references that I used during this presentation, and thank you for listening.